Okay, hi guys. So I'm going to continue with aspects of chemical change. This is going to be in the summative assessment up until the limiting reagents. Okay, so when we get there, I'll tell you. Okay, so this is really still revision. So remember your number of moles. 1 mole is equal to 6,02 times 10 to the 23 particles. So if I have a mole of people, that means I have 6,02 times 10 to the 23 people. Okay, here is the formula. The number of particles is a capital N. Okay, is equal to the number of moles times 6,02 times 10 to the 23, which is Avogadro's number. So it's moles is equal to mass of a molar mass. That's the formula you should be familiar with. Okay, number of particles, N, there it's the same thing here. But this time we're looking at, I've made moles the subject of the formula. So your number of particles divided by 6,02 times 10 to the 23 will give you moles. Remember that if you are given molecules, so in other words, you are given, I say to you, how many particles or how many moles, or no, how many particles are in 5 moles of water, okay? You use this and you're going to get, because it's a molecule, you're going to get the number of molecules, okay? If you are asked for atoms, you then go a step further. So how many oxygen atoms are in 2,3 moles of K2Cr2O7? So we know the number of moles, okay? If we get the number of particles, we are going to get how many molecules, because it is a molecule, okay? So I can do, wait, let me go this. Okay, so N is equal to number of moles times Avogadro's number. Actually, Avogadro's number does have a symbol as well, if you remember. It's capital N with an A there, capital A as a subscript. Okay, so that's going to be 2,3 times 6,02 times 10 to the 23. And we're going to get 2.3 times 6.02 times 10 to the 23. And I'm going to get 1,38 times 10 to the 24 molecules. Okay, again, sorry, that's molecules. Okay, because K2Cr2O7 is a molecule, and you've been told you have so many moles of those molecules, the answer here will be in molecules. You now then have to take a next step to say, well, how many oxygen atoms are there? Okay, so, sorry, my cat has arrived again. So what we're going to see now is in each molecule, we have 7 oxygen atoms, okay? But I have so many molecules. So if I times it by 7, I'm going to get how many atoms there are. So 1.38 times 10 to the 24 times 7, and I get 9,66 times 10 to the 24 oxygen atoms. Okay, so just remember that if you're asked for atoms, just check. If they give you atoms, you can stop there. If they give you a molecule, you have to go a step further, and you times by however many you have in the atom. In the molecule. Okay. Now, molar volume, MV, M with a little v. Now, this is a volume of 1 mole of gas at STP is called the molar gas volume. The same number of moles occupies the same volume at STP. Do you remember STP? STP is standard temperature and pressure. And that is your, oh my gosh, I've gone blank. STP, I'll come back to that. Let me just get that. Oh, while you're waiting for me, I want you to please make sure that you have a data sheet for your summative assessment. Okay, because it's going to be hard for you to read the answers and then have a look at a data sheet online as well. Please be honest and make it a blank one. Okay, I'd appreciate that. So STP. Sorry, I've gone past it. Okay, so your STP is 273 Kelvin. Remember, there's a Kelvin scale, which is the same as 0 degrees Celsius. Okay, and you get a pressure, so that's your temperature, and you get a pressure of 1,01 times 10 to the 5 pascals. These are on your data sheet, so you don't actually have to learn them off by heart. You can look on your data sheet. Those are the values for standard temperature and pressure. Okay, so if you have standard temperature and pressure, so those that temperature and that pressure, you will get the same number of particles. So whether it's atoms or molecules, you're going to get the same number of particles and the same volume. So same moles, same volume at that STP. Okay. So it's like saying, this could be like saying neon. We take neon gas and we take oxygen gas. Okay. We have the same amount. All right. I put neon in one balloon and I put oxygen in another balloon. Right. And I get them to STP. When we measure the sizes of the balloon, they will be identical. That is what it's saying. Please, I want you to remember, though, that yes, we're going to use moles, and we have a volume, and then we have a molar volume, and the molar volume is constant. Now, the molar volume doesn't always have to be 22,4. It is only 22,4 if the conditions are STP. If you have a different standard temperature and pressure, you will have a different molar volume, okay? Please remember, you can only use this formula. This is like a default formula that everybody goes to, and I don't know why. I think it's because you've already got a value for it, 22,4. The molar volume is only used if you have a gas. Okay, you can't, if you have liquid, aqueous, or a solid, you can't use this formula. It's only for gases, right? And they have to be at STP to use the 22,4. Okay. I remember there was a question once in another prelim paper where the examiner gave them a different temperature and pressure, and they had to work out the new molar volume of because she gave them all the volumes and the number of moles, and they had to work out a different molar volume. So be careful. The 22,4 is a constant, but only with STP, only at those temperatures and pressures. Okay, please make note of this. Okay, Avogadro's law states that at the same temperature and pressure, equal volumes of gas contain equal numbers of molecules. That is what he says. So what we've done is we've gone, okay, well, now we're going to use this standard temperature and this standard pressure. And that means the volume is always going to be this. Okay, but it doesn't always have to be that. If it's different temperatures and pressures, but they are constant, it will have a different molar volume. Okay, so please, if you're getting confused, rewind me and listen again. Okay, so volume ratios. Now, again, when you have a balanced chemical equation, this will only work. This comparing your ratios in terms of volume can only work if you've got all gases. It is at STP. Okay, then I'm not saying that you can only use this formula when you have all gases. It just must be a gas, whatever you're using here. But to use the ratios of volumes, they have to, all the reactants and products have to be gases. So this is a 1:3:2 ratio. So we can say, oh, well, if I have 20 centimeters cubed and this whole thing is at STP, then I know it's a 1:3. So I times by 3. So I get 60 centimeters cubed. Then this is a 2 times by 2. This is a 40 centimeters cubed because it's all at STP, and so I know we have a constant here. Okay, it only happens if the whole system is at STP and the reactants and products are all gases. Right, concentration. So concentration, and this comes in with that reaction rates. Remember with the concentration, it's the number of moles, which is essentially also the number of particles per volume. Okay, that's what gives you a concentration, not just the number of moles. Okay, like I say, you have a million people in South Africa, let's say. Oh, that's hardly, I mean, that's really not concentrated. But then I say to you, we have a million people at Ritvlei. That is concentrated. Okay, so it has to do with the volume, the amount of space they take up. Okay, so here we have a high concentration because we've got more moles in this volume compared to here we have less moles in that there. So moles and decimeters cubed. Please make sure that you convert to decimeters cubed. Concentration is mole per decimeter cube or a capital M. We never use this though. Okay, but if you see it, it means the same as mole per decimeter cubed. Okay, so 25 grams of NaOH is dissolved in water and made up to a volume of 250 centimeters cubed. Calculate the concentration. So we've got 25 grams of NaOH. Okay, we have a volume of water, which is 250 centimeters. Blah, looks terrible. We need a decimeter, so we divide by 1,000. Divide by 1,000. Okay, so we get, and that means you're just moving out comma 3 spaces, 1, 2, 3. So 0,250, and you can drop the last 0 if you want to. Decimeters cubed. Okay, so I want concentration. C is equal to N over V. Got a problem. We don't have moles, but we do have a mass. So we know we can get our moles, by using this equation. Okay, so our number of moles is 25 grams divided by sodium is 23. Oxygen is 16. Whoops, I'm just going to put it plus, sorry. And we have hydrogen, which is 1. Okay, don't multiply them, please. Add them. I don't know why I did the brackets. Okay, so 25 divided by, and I'm just going to use brackets here, 23 plus 16 plus 1 is equal to 0,625 moles. Okay, so that's how many moles we have. So I can go back to this equation now. Remember to always put your equation and make sure you use proper units. So 0,625 over 0,250, and my concentration is 0,25. 2,5 mole per decimeter cubed. Okay, right, so that's working with concentration. This is all just revision. Okay, what mass of KOH would make a solution of 3 molar? See how they did it, how I did it there. It's basically a lazy way to do it because I don't feel like typing mole per decimeter cubed because you have to keep using the superscript button. Okay, if 500 centimeters cubed, so immediately we're going to make that to a half. Okay, half a decimeter cubed, because remember, centimeter cubed is 100th of a meter cubed, so that is 500 milliliters, and that makes half a liter. And a decimeter cubed, deci stands for 10, so it's 1/10 of a meter cubed. Okay, so C is equal to N over V. We want to know the mass, so we need this equation, and so we need our number of moles. Okay, so we know that, and we know the concentration is 3, and we have a half. So timesing by half is like dividing by 2. So we get number of moles is equal to 1,5 moles. Okay, I can then put it there. 1,5. I need to get the mass. KOH. K is 39 plus 16 plus 1, because it's K plus oxygen, it's potassium plus oxygen plus hydrogen, and we're going to multiply them together. So my mass is 1,5 times 39 plus 16 plus 1, and I get 84 grams. Okay, so if I want a concentration of 3 molar and I want half a liter of it, I need to measure 84 grams of KOH. All right, so remember this. I'm sorry I couldn't print it in color now, but I'm sure you can if you want to. So this is that island system. So it's, remember, you can get anything, any one of these, by getting the moles. When in doubt, mole it out. So I'll give you mass, you work out moles to get volume, only if it's at STP. Okay, at STP. If I give you mass and you have to get concentration, number of particles, mass. You can get anywhere as long as you step into moles first. Okay, all right, this does look like a lot of work, but it's really not. If you have a look here, it's 1, 2, 3, 4 questions. 1, 2 questions, 1, 2, 1, 2, 3, 4, and this is multiple choice. Okay, so I want you to do this now for me, please. You should have more than enough time because this was only 17 minutes. So you've got more than an hour to do these questions for me. I will be available on Google Meet if you'd like to discuss anything that's confusing you, or if you want to type a question, please do it on Google Classroom so I can answer you on there. All right. Okay. Please talk to me if you are not getting something. All right. Love you lots.